We'll start out with some geometric power series for the first couple days. I'm going to teach days number 1 and 2 kind of together in the same lesson. Really, it's probably more of a day and a half lesson, and I'm not sure how it's going to pace. So we'll just do them both. All right, the first couple examples are straight out of Algebra 2. Find the infinite sum. Again, less experienced students are going to think that the answers are both infinity, but they would be wrong because both of these series are converging. And since r is less than 1, or I should say r is between 1 and -1, they have answers. And remember that the formula that we have been using for quite some time now is down here. Sum is term 1, which the book calls A, over 1 minus r. Remember, r is the common ratio. That's what you're multiplying by each time. All right, so here in this problem, number 1, r, as you can see, is 1/2. If you skip ahead to number 2, r is going to be, this is a little tougher to tell. You can pick any number and just divide by the number in front of it. 36/48 will be 3/4. If you didn't like that, 27 divided by 36 is also 3/4. All right, so regardless, you're good. Let's get both of these answers. We'll come back to number 1 again. Using the formula, we have term 1, which is the 80, over 1 minus r. This is 80 divided by 1/2. That's the same as 80 times 2. It's going to add up to 160. You will never get past 160. Even if you could make it to infinity, you'd be at 160. So that's the actual answer. All right, number 2, same formula. To find the sum, you're going to take term 1, which of course in this case is 64. You're going to go 1 minus r, so 1 minus 3/4. Again, that's 64 divided by 1/4, which is the same thing as 64 times 4. And that's going to give you 256. 256. Now, of course, they're not all going to come out to whole number answers. I just gave you a couple really stellar problems. But that's the formula. And today, we're going to take this old formula that we know and love, and we're going to use it to generate what we call geometric power series. And that's why I wanted to do a quick review so it was fresh in your mind. All right, here in number 3, when you look at that problem, f of x equals 4 over x plus 2, you probably, at least first glance, wouldn't say to yourself, oh, that's geometric power series. This sort of takes some training. We're going to try to make it look like the formula that we just used, that term 1 over 1 minus r. So the first thing I'm going to do is I'm going to switch the order around in the denominator. So obviously, instead of 4 over x plus 2, I went ahead and made it 4 over 2 plus x. Except instead of writing 2 plus x, I got a little sneaky. I went 2 minus negative x. Normally that we consider that backwards or unsimplified. But remember what my goal here is. I'm trying to make this look like the geometric formula. So I do need this minus here in the middle. I also need it to start with a 1. Right now it starts with a 2. No problem, I'll just divide everything by 2. So you're trying to make it look like 1 minus. And that's what will dictate what steps I choose in my algebra. All right, when I take my green equation and on the right side I divide top and bottom both by 2, I arrive at this. And now you can see that this does match the form that I'm looking for. I've got the 1 minus in the denominator. So now in this case, I can tell you what a is, or term 1. It's going to be 2. And r is negative x over 2, or negative 1/2 x. And now I'm simply able to write it as a geometric power series. You can see the r right here, because that's the part that's being taken to the n power. Here is the first term, term 1, that's the 2. And I like to use n equals 0 because if you plug a 0 in here, then the first term is the 2. You get 2 times something to the 0, which is 2 times 1. Our book does show a method for long division on page 672. I do not want you doing the problems that way. You will get the same answer. You can check it out if you want, but it's not part of our curriculum. And to be honest, it's a lot stranger, I think. So I would just stick with this. Use the formula that we know and love from Algebra 2. Term 1 over 1 minus r. And just make the problem look like that first and then go get it. All right, we're going to try one from scratch. Going to try a couple of them from scratch now without the step-by-step hints. Here's number 4. Okay, we have 4 examples left. For number 4 and 5, I'm going to have you guys do a geometric power series, and I'll let you have it centered at 0, which is being nicer. And then for the last 2, for number 6 and 7, I'm going to have it centered somewhere else. We'll see how that plays out. All right, so on this one, first things first, you have to have a 1 minus in the denominator. There's no ifs, ands, or buts about it. This 8 is not acceptable. It has to be 1 minus. So no problem. I'll just divide both numerator and denominator by 8. That way I get what I need. If you divide this by 8, it'll be x over 4. And obviously if you divide 7 by 8, you have, 7/8. Let's not make this too difficult, right? All right, now we are in the proper form. We know what term 1 is. It's 7/8. We know what r is. It's x over 4. All right, we're ready to write our answer. And it's going to be this. We're going to do the summation. Obviously, infinity up on the top. Like I said, I like to start with n equals 0. That way, when I put the 7/8 in, and the rest of it is to the nth power, I know that it's going to be to the 0 power to start off. And then the r just gets dumped in. The x over 4, because that's what you're multiplying by. And that will be our answer. And if that answer seems reasonable, it's because it is. Oh, yeah. There we go. All right, on to number 5, another geometric power series, also centered at 0. Let's get after it. All right, we want to turn it into a geometric power series. It has to start with 1 minus. Right now that's a 5. That's not acceptable. So we're going to divide everything by 5. That way we have the 1 that we need. This will be 1/5. And this will be plus x over 5. But remember, we also need it to be 1 minus r in the denominator. So I'm going to change this plus x over 5 to minus negative x over 5. Let's do that over here. All right, excellent. That means that term 1 will be 1/5. And the r will be the negative x over 5. So I'm ready to write my summation. All right, as always, we're going to go from 0 to infinity. Term 1, that's the 1/5. And then the r is the thing that gets treated by the exponent. There we go. What a glorious answer that is. The only thing better than getting a glorious correct answer is checking it with the back of the book and making sure that it's right. And getting that feeling of satisfaction. Whoa. That's not my answer. Not exactly, at least. But you know what? I am correct. And as I said in parentheses down there, it's often customary for textbooks to express the answer like this. They like to make it look like an alternating series, so you can see the blinker light, you can see the -1 to the end. So I'm going to go ahead and show you that my answer is the same as what you will probably see in the back of the book. Here are the linking steps that you can use to show that they are the same. I'm going to take this right here, this negative x over 5 to the n, and I'm going to split it up. Okay, the 1/5 comes down unharmed. This can just be split into two separate parentheses. That's just basic algebra 1, nothing fancy here. The negative 1 to the n, as you can see, makes its way into the answer. Also from algebra 1 is take this and rewrite it as x to the n over 5 to the n. Do that out here. Okay, so that just got replaced. I'll cover it up so I don't think there's two of them. And you can see that the x to the n is also in the final answer up top in the numerator, as it should be. But here's the weird part. This 1 is invisible, of course. I'm not going to look at it. I already have other things up in the numerator. But this other lone 5 is 5 to the first. And when you have 5 to the first times 5 to the n, that's 5 to the n plus 1. And so again, a lot of times the textbooks will take our answer and they'll change them around a little bit to make them look a little bit more like an alternating series, which is fine. Now, do you have to do this? No, you do not. I am fine with, obviously, the book-style answer. I'm fine with this. They're equally good in my mind. My only concern is this. If you're on an AP exam and the answer choice looks like an alternating series, are you going to be able to pick it? Are you going to be able to look at your red circled answer and say, oh, that's the same as that other answer? If you can say yes to that, then I'm cool. All right, we have two more examples, number 6 and number 7. That'll complete the first couple days of section 9.9, the geometric power series portion of it. In both problems, number 6 and 7, this time we're not centered at 0. We're centered at C, and C happens to be 3. So this is going to take a little bit more Algebra 1 ingenuity on our parts. Obviously, we're going to have to rewrite this original because this is centered at 0. There's no parentheses. I need it to be centered at 3. So first things first, it must be centered at 3. There are no other ways to do this. I also want a minus in front of it because I want it to look like, 1 minus r. How in the world am I going to make this transition? Well, I'll throw a 3 in front. If you take a look at this, you can see that I really cleverly rewrote 6 minus x down here because this is the minus x. That's plus 3. There's another plus 3 in front. That's 6 minus x, but it looks more geometric. And by the way, here's the 2 in the numerator, untouched. So we're looking a little closer to what we need it to look like, but I got the all-important centered at 3 that I had to have. All right, speaking of have to have, this has to be a 1. There's no debating it. That just has to happen. So I'm going to divide everything by 3. Numerator and denominator both being divided by 3. Dividing by 3 gives me this 1 that I really need. Over here, you're going to divide by 3. Again, let's keep the parentheses on so we know that the distributive property is alive and well. And then the numerator, you have to divide that by 3, so that'll just be 2/3. And now, finally, we have it ready to roll. That is geometric. And so we can give ourselves a summation. Okay, as always, we're going to go from n equals 0, being the index, up to infinity. And term 1 is 2/3, so that'll go first. Inside the parentheses will be the r. And that's being taken to the n power. All right, fantastic. So that is it. Like I said, there's a bunch of different clever ways that you can write this. I'll show you another way that sometimes you'll see the textbook do this as well, even though our answer is perfectly fine. Let me move our answer over a little bit to the left. Sometimes what you'll see is the textbook will take this 2 and kick it out front. And they'll write it here. And that will leave you with a 1/3. And then they take this parentheses to the nth power and they split it up. And so they say, okay, that's x minus 3 to the n over 3 to the n. Oh, but wait, here's a 3 to the first. So they say over 3 to the n plus 1. I just want you to get used to seeing that. A lot of times that's the way you're going to see the answer written. Both of them are equally correct. So just be advised. All right, for number 6, we're looking good. We did this so far. We found a power series for the function centered at c. But here's the dreaded word and we have to do an interval of convergence as well. And in fact, while I'm still here, remember, since these are geometric, I know that r, or at least the absolute value of r, just simply has to stay less than 1. So when we ask for the interval of convergence on a geometric power series, it's easier. You just take the r, and you say, hey, r, x minus 3 over 3, yeah, you. Your absolute value needs to stay less than 1. Okay, again, I'm going to take this to a new sheet of paper just because I need some room. That's what's really cool about having a geometric power series is you don't have to use the ratio test to figure out, what this is. You already know what r is, and you know the r has to, converge. So it has to be between 1 and negative 1. In fact, let me do that now. So your absolute value being less than 1 implies that you yourself have to be between negative 1 and positive 1. Okay, I'm going to triple all 3 parts. That'll just give me an x minus 3 here in the center. And since I'm multiplying all 3 of them by positive 3, no sign flippage. Signs are all going to stay faced the same way. And I'll add 3 to everything. Plus 3 in the middle to knock that out. And plus 3 to the ends as well. All right, so I have my unofficial interval of convergence. Again, I have not tested the endpoints yet. I have to test the 0 and I have to test the 6. I think I'll go back a slide to where I actually have the equation written, and we'll try both of those in. All right, I think I'll just try it right here in this green circle. What if x was 0? Well, that would give me, obviously this 2/3 doesn't matter. It's not going to affect its converging or diverging nature. I'll just kick that out. But the rest of it, if you had 0 minus 3, that'd be negative 1 to the n. That's just going to oscillate forever. If you tried the 6 in there, so make that a 6. 6 minus 3, that'd be 3 over 3. That's 1 to the n. That's going to stay 1 forever. And so in this case, they're both going to diverge. And since they both diverge, you don't need equal to's on either one of those. This unofficial answer can now become official. So x has to remain between and not equal to 0 and 6. Or if you prefer, you could go interval notation. But those represent the interval of convergence. All right, now I have especially great news concerning geometric power series. If the series is geometric, you do not have to test the endpoints. Wait, what? Yeah, what I just did was completely unnecessary. For geometric only, now don't get me wrong, normally you have to test the endpoints, but for geometric, you don't have to test the endpoints. They will always, always, always diverge. And the reason why is the endpoints come from r being equal to 1. Think about this. If you plug the 6 in, right here, the reason that it's a border point is it's going to make it a 1 inside. If you plug the 0 in, the reason it's a border point is it's going to make it a negative 1 inside, and then the absolute value would change it. If you are multiplying by 1, think of a number in between 1 and 10. I don't know, 8. Let's say you get a series, and you started with 8, and you kept multiplying by 1. Plus 8, plus 8, plus 8. That's not going to add up to anything other than infinity. That's going to diverge. It's not getting smaller. Same thing if r was negative 1. 8 plus negative 8 plus positive 8 plus negative 8. That's going to oscillate back and forth between 8 and 0. Right? So you're not actually heading towards 0. You're bouncing back and forth. In both of those cases, the nth term test says, just simply divergence, or simply curly parentheses. So once again, geometric, if I ask for an interval of convergence, you do not have to test the endpoints. Everything else, all the other regular series, yeah, absolutely. All right, one more to go, number 7. Again, we want you to find a power series, but the centering point will not be 0. It's going to be somewhere else. And in this case, it's going to be positive 1. Let's go there right now and get it done. All right, so I need to make this look like a geometric power series. Again, I don't like the way it looks. I've got to flip it around. Oh man, this is the toughest part for me personally. All right, I know that I need it to be 1 minus, so I know that this 3 needs to come first. And then the 2x needs to come last, so 2x. But you can see what I'm doing here. At the same time, now I haven't changed anything yet. Oh yeah, I have. I flipped the subtraction around. That's no good. We'll have to put a negative on the 4. There we go. All right, so here's what I've done so far. I've multiplied numerator and denominator both by negative 1. Okay, covering my tracks. The 4 became a negative 4. This positive 2x became negative 2x, and I put it at the end, along with some future parentheses that right now aren't doing anything. And the minus 3 became a positive 3, and that is now in the beginning of the denominator. All right, so far so good. Here's the big deal. It needs to be centered at C. It needs to be centered at 1. I must have an x minus 1 here. It's not negotiable. I have to have that. The only problem is this denominator no longer matches the thing I started with, which I should probably rewrite as 3 minus 2x since I multiplied by negative 1. All right, those two things do not match. They are not equal to each other, and they better be equal to each other, or I'm changing the problem without meaning to. So let's see what disaster I have created. If I distribute this, that's a 3 minus 2x, and then negative times negative will be plus 2. So really, I have a 5 minus 2x. Is what I had. But it needs to be a 3 minus 2x. That's what the problem started with. This is what I have now. Mine is too large by 2. So I need to take away 2. Well, that's easy enough. I'll just make that lead off 3 into a 1. Which, coincidentally, is what I needed to be anyway. That was just a stroke of luck, so I won't have to divide later. But now, since I'm leading off with a 1, what I have here circled is 3 minus 2x. That does match what I used to have, and so I'm okay. Oh, wow. All right, let me rewrite. F of x is going to be equal to negative 4 over 1 minus 2 quantity x minus 1. All right, that is in geometric format. Term 1 is your negative 4 up top, and your r, or common ratio, is going to be this thing. You can also call it 2x minus 2 if you prefer. I'm going to leave it like that. All right, so we're ready to write the power series. Here it is. It's the summation, as always, from 0 to infinity of term 1, that's the negative 4, times r, I'm going to use some brackets since I've got little extra parentheses here, times r to the n. Wow. All right, that is correct. That's the first part. We have found a power series centered at 1. You can see it is centered at 1. I got the x minus 1 in there still. And now we simply have to find the interval of convergence. So again, I'm going to go to a separate page. I will take my answer that I just found, and we'll work with it. All right, good. Okay, there's my power series that I just found. And now we want to find the interval of convergence. Well, again, good news. This is geometric, so we don't have to test any endpoints. We just simply need to take the r, which is this right here, make sure that it stays between -1 and +1, and solve it. I'm going to go ahead and divide all 3 parts by 2. You could also distribute the 2 if you are more comfortable with that. And then I'm just going to add 1 to all 3 parts. All right, so x has to be between 1/2 and 3/2. Normally that would be the unofficial answer, but again, we know that since this is geometric, the endpoints are going to diverge. So actually I am finished, and that is our official interval of convergence. Good solid job, everybody. I hope that made sense. And we'll see you next time for day number 3.